Hello everyone, I am Yves Delabroise, software architect for the KINGSTAR software at Interval Zero. And today I'm going to be talking about controller integration for machine control. Machine controllers are based on standardized controllers such as PLC, CNC, motion boards, robots, vision, and HMI. But inside a machine, you usually don't use only one controller. You have classic pairings, such as a PLC plus a CNC or a PLC plus a robot, with additionally an HMI. But now with new machines, with more complex and more flexible machines, you have new types of pairings, such as CNC plus robot or vision plus robot, which require more advanced integration of the two controllers. It is not simple to just make the different programs, each controller independently, and then have them talk to each other with IOs. So first, why integrate the multiple controllers? One of the reasons can be performance. If the controllers are properly integrated, which means that they talk to each other with variable sharing, remote procedure calls, status sharing, then you can close the loop. You could have, for example, with vision and robots, you can have the robot using the results of the vision to process its move directly. The second very important reason is ease of development. At the moment, when you have two controllers, you have two development environments and two programs. Then you have to find a way for those programs to communicate and share information. This is quite painful. So if the two controllers can talk to each other, having one controller control the other, then you can simply have one program for the machine, which is much simpler to maintain. And the last reason is the ease of use for the operators and customers. Because one main controller means all the tools for the operator and for the maintenance are in one location, usually the location where you will have the HMI. And those tools can do everything, such as update, configure the different controllers, and even the hardware, the drives, the IOs connected to these controllers. How this is done? Well, the initial idea is that with these new computers that are very powerful, we could run everything inside one PC-based controller. So it would be a controller that does motion, robotics, vision, PLC, CNC, and everything. This ended up being a bad idea for two reasons. First, you rarely need all these functions, which means the controller hardware will usually be oversized and overkill for the machine. The second one is that it is often that you want to repurpose your hardware. You have a machine, you have two machines that talk to each other. For example, a machine that has a robot for loading and unloading. You could switch the loader unloader to a different robot, to a smaller one, or to an XYZ combination. You want to reuse this robot somewhere else. Well, if you only have one controller, this robot cannot be reused. It doesn't have a controller. It becomes useless, which is a waste for reconfigurations. So the idea became to have independent controller that talk to each other, which means each controller has its own software, its own control software, its own control stack, which can either be deployed on the same computer as others or on separate computers. You could have a machine with a robot, a vision, a CNC that has three software controllers sharing one field bus. And then if you need to separate the robot, you could take the software, move it to another computer to control the robot standalone, or to another machine that has its own controller and that will now control this robot. This way, you do not need to buy new hardware, buy new software, and things like that. You can just reuse what you already have. To make this flexible, you need to have the same architecture, whether you are local or remote in terms of hardware. How do these different controllers talk to each other? Well, instead of reinventing everything, we use protocols and definitions that are already here. There's been a long time use of PLC and CNC together, or PLC and robot, which means function blocks and functions have been defined in a PLC interface to control a CNC or to control a robot or to control vision. These function blocks can be reused as remote function blocks, which means the main controller will use these same interface to send functions to the robot or to the CNC or to the vision controller to give it instructions. How do we send this information? Same thing again. We reuse the most common field bus in the automation, the standard OPC UA, which allows communication between the HMI and the PLC, or the HMI and the CNC. So we reuse these components that are already existing in the different controllers to allow them to communicate in a more efficient way. With this result, you can have one main controller, which usually has a PLC interface, which will control the CNC, the robot, the vision, and itself, with one single program for the whole machine. But each controller itself will execute the safety logic, the interpolation logic, which means when you want to reuse it, you can just take the robot, connect it to another PLC or another main controller, or even use it standalone with its own internal interface. How is this done internally in the controller architecture? Well, for this you will need a real-time operating system for the control piece, for the real-time control piece. And in most cases, you will also need a general purpose OS. This is if you want to have an HMI or tool options on this controller. To allow the controller to have multiple software stations, local or remote, you will need a subsystem that controls the field bus and allows multiple clients, multiple control clients, to access the field bus to talk to the different controls. This subsystem will of course be in real time connected to the internal network, for example EtherCAT, and to the controller-to-controller communication bus, OPC UA. It will allow controllers to send commands to one another, whether they are local or on different hardware. It will also allow the tools to communicate with the controller, no matter if they are remote or local, and to connect also with the field bus itself, the drives, the IOs, and other hardware which is connected. So this subsystem will be in both real-time and non-real-time environments and allow remote procedure call and variable sharing for all its clients, which will be both local and remote over OPC UA, accessing the field bus and the local controllers. So in conclusion, when you are now building a new controller, which you plan to have multiple different usage, you will need to consider this new architecture for it to be allowed to be integrated, which means it has to be PC-based. If you make a hardware-based controller which is on a fixed hardware, it will only be usable for a single purpose. If you want it to be used for different purpose, it needs to be able to interconnect with other controller and to receive additional tools and additional software, which means it has to be PC-based with an RTOS and a GPOS. It will require a subsystem to connect the OPC UA and the machine field bus to the controller, the local controller, and to the remote pieces. When we developed our product line KINGSTAR at Interval 0, we had this in mind. So we built KINGSTAR as a subsystem which controls an EtherCAT bus and exposes information to multiple local applications, whether they are real-time or non-real-time, and through OPC UA to remote applications. It also pre-integrates a PLC if you want this to be the main controller to send functions locally to controllers or remotely over remote procedure calls. Thank you for your time.